Okay, now in this video lecture, we can talk about the product measure. So the product measure is to say if we can assign measure to sets of a certain space, and we can assign measure to sets of a certain other sample space, then we can look at the Cartesian product of these sets, and in the Cartesian product of these sets, we can consider subsets there and assign measures to those subsets. So this we start with a lemma before we can establish the theorem that states the existence of this product measure with the properties that would like it to have. So we know already from the previous video lecture that if we fix a point here x and we have a set E which is a subset of the Cartesian product, but not just any subset. In fact, E is measurable with respect to the product sigma algebra, the sigma algebra of the first space and the sigma algebra of the second space. And what we have seen already is that once we fix x, any point in the first sample space, then the set that we get in the second sample space that we call Ex, that this is measurable. And now, differently from the previous video lecture, we're introducing a third element here. Now we don't have just a space, a set of points to take the product, or a sigma algebra to take the product. There's some measure here now that we're going to incorporate into the game, and adding to the previous lemma that which said each Ex is an element of F2. Now, because it's an element of F2, we can assign a measure to it. And what we are going to see now is that this function that for each x assigns the measure of the section at x is measurable. Okay, yes, this is making our brains rotate in a very high speed. I appreciate that, yes. So again, what is measurable? Yes, for each point x here that we fix, we can look at the section. This will give us a subset of the other space. We can measure that set, meaning we can compute nu of that section. This will give us a number. That number, it depends on x. So this function that associates to each point x this number, what the lemma is saying is that this function is F1 measurable. Okay, then of course by symmetry we'll have that the other function, if we do the opposite business, we fix some point y here and we fix y here, and this will give us some EY that we can measure. And we can compute the measure mu of EY. So this function then of course will be measurable as well for the same reasons. So let us just focus on the first one. This is what the lemma is saying. The lemma is saying if once we take the measure of the section at x and consider the function that to each point x assigns that measure, this function, which is a function from omega 1, because x is in omega 1, to r plus, or even r plus including infinity, okay, this is a measurable function. Before we prove the previous lemma, let us skip and go here to how will that lemma mostly going to be useful. It will be useful to establish the following, and this is already a key fact in the theory. It is called product measure. Okay. What is this theorem is saying? It is saying if we have two sigma finite measures, and sigma finite is important here, these things start to degenerate when we leave this world. At least the part of uniqueness can be lost. So we have two sigma finite measure spaces. Okay, one measure space, another measure space, they have nothing to do with each other. You can think this measure space is a probability space that represents a certain random experiment, and this is also a probability space which represents a different random experiment, possibly the same. Or you can think one is whatever set you like to compute integrals on, so it's just any measure space. Your favorite one would be the real line. And the other one is also just one where we can compute integrals, can be also the real line. And here we are talking about then about the plane when we take the product. Or it can be a combination of both. It can be that here we are doing something random, and here we are computing integrals that depend on the outcome of that random thing. We can use this space then to compute integrals that can be related to some random experiment. So these are two measure spaces. They can be any measure space in principle. And what is this theorem saying? It is saying it is possible there exists a unique measure on this sample space, omega 1 cross omega 2, with the product sigma algebra. There's a unique measure with this property, that the measure of a rectangle is the product of the measure of both sides of that rectangle. Okay? And if mu is a probability measure, and nu is also a probability measure, then this product measure here is just saying we can perform both of these experiments independently. It is what the product measure is representing, because we are asking what are the sets, what is the probability that in the first experiment we observe A and in the second experiment we observe B, and we're getting, well, it is the probability that we get A in the first experiment times the probability that we would get B in the second experiment. So this is related to independence when we're talking about probability spaces. So again, the theorem, the main part of the theorem that will be used most often is there exists a unique measure. So we give it a name. We denote it like by this funny product here. So it's a product with a circle around it. So it exists and is unique, a measure with this property. Now the second part of the theorem, which we don't use as often in practice, but we also do use it, is that we can compute this measure in two different ways. The first way is we let x be a variable. We take the section at x, we compute the measure of that section. So this means if I can zoom in here to make a picture, this means for each x that we fix, we can consider a set E, for any set E that is in this product sigma algebra. We can compute this measure here. This will be nu of Ex. This is a function of x. And for that function of x, we can integrate that function of x by the measure mu that we have here in the first space. Okay, so we integrate on the first space a function which is given by computing the measure of the section at x for each point x and integrate it against the measure that we have in this first sample space. Or we can do by symmetry, we can do the same here. We can for each y, for each fixed y here, we can take a section, then we can take the measure of that section. We can make the measure here, mu of Ey, and we can integrate that over y. So it means we take this section, then this section, then this section, this, and we add them all together. This is what this integral here is doing. So we integrate on the second variable, we integrate this function that assigns to each y the measure of the section. And what this theorem is saying is we can compute this measure like this or like this. But most important is is that then there exists a measure that has this property here. So it factorizes. It's a measure that factorizes when the set under consideration is a rectangle.